Hey guys, today's video is about Millman's theorem. In this video, we cover a little bit more about the theorem, the person who proved the theorem, and what type of circuits this theorem can be applied to. The theorem was brought forth and proved by Jacob Millman. Basically, it's used to compute the voltage at the end of a circuit made up of only branches in parallel, and is very useful in the study of operational amplifiers, which I will be covering in my next videos. It is applicable only to solve the parallel branch with one resistance connected to one voltage source or current source. But don't worry guys, there are a lot of a set of rules that are used to simplify branches that contain more than one resistors or more than one current sources or voltage sources. So using those set of rules, you should be able to simplify any branch circuit into either a series combination of a voltage source and a resistor, or a parallel combination of a current source and a resistor. Today's video we will be solving this circuit using Millman's theorem. And basically what we're looking for is the voltage across the load resistor and the current flowing through it. I've redrawn the circuit in a different way, emphasizing on the common between the branches, this line, the common, which is connected to ground. And then these points will be used to determine the voltage and to determine the current across this load resistor. Using Millman's theorem, we found an equivalent voltage based on a formula which says that for every parallel branch, you should be able to identify the source voltage, or the source voltage. You should be able to identify the resistor that connects to a given point where you're looking to find or determine a voltage. When you know that, you should do the same thing for all the branches that connect to that point. So E equivalent will be equal to E1 over R1, which is this voltage source which connects to A through R1. So E1 over R1 plus E2, which is this. Notice this is a negative voltage. Why? Because this end, the resistor is connected to the negative end of this voltage source. So it is seeing this voltage source as a negative one, as a negative voltage. So you see this as negative 16 volts connected to R2, which is 4 ohms. And then you have 8 volts connected to R3. So you have E3 divided by R3. And you divide that by the sum of the reciprocal of each resistor, which is going to be 1 over R1 plus 1 over R2 plus 1 over R3. When you replace the values, you get E1 over R1 will be 10 over 5. E2 over R2 will be minus 16 over 4. Minus why? Because E2 is negative from here. So E3 divided by R2 will simply be 8 over 2 divided by the sum of reciprocal of each resistor. You get this. And this is an extension of resistors in parallel. So that's why you get, 1 over the sum of the reciprocals. Now, when you simplify this is voltage over resistance. So this gives you current. So 10 over 5 is going to give you 2 ampere or 2 amps. 16 over 4 will give you 4 amps, negative. 8 over 2 will give you 4 amps. And then 1 over 5 ohms will give you 0.2 Siemens. 1 over 4 ohms will give you 0.25 Siemens. 1 over 2 ohms will give you 0.5 Siemens, or 0.5 per ohm. Then you divide this, you get your equivalent voltage as 2.11. What this means is that all of these parallel branches can be replaced with a single branch where the voltage is going to be 2.11. Now let's find the equivalent resistance that is going to be used to replace. That can be the equivalent of this, these three resistors, and that basically is going to be, finding the equivalent resistance from a parallel set of resistors. So you just apply the formula. So this, and you get 1.05 ohms. And remember, when you determine the equivalent resistance of a set of parallel resistors, that value is always going to be less than the smallest resistor in the parallel set. So in this case, the smallest resistor in this parallel set is 2. And we find that the equivalent resistance is 1.05, which is less than 2. It is very important, guys, when you're solving electrical circuits. The value should be consistent with the theory. This value should be less than 2. If it is more than 2, then it's probably a calculation error. Now, if we redraw this circuit, right? If we redraw this circuit, replacing all this voltage, which is with an equivalent voltage source, and replacing all these resistors with an equivalent resistance across these 2 points, across this load resistor, what we get is E equivalent, right? Which is 2.11 volts, okay? And then we get RL, which is 3 volts. Now, don't forget what we're looking for, guys. We're looking for IL, okay? So, this is a simple, series circuit. We need to find IL. We have 2 resistors in series. So basically, IL is going to be the voltage source, which will be 2.11, the sum of voltage sources, algebraic sum of voltage sources across around this closed loop, which is simply this, divided by the sum of resistances, which will be 3 plus 1.05, which will be 4.05 ohms. And this gives you 0.52 amps. Now we have the current. This is the same current flowing through R equal, and the same current flowing through the load resistor. Now we have the option to find VL. We can find it one of 2 ways. The first one is through a voltage divider, where basically you specify the voltage you want to, the resistor across which you want to determine the voltage, which in this case will be RL. So it's just RL over the sum of all resistances, in the loop, which gives you R equivalent plus RL. The sum of resistance, because this is, this is a series circuit. If you need to find RL, you just simply specify, the resistor across which you want to determine the voltage, and then you divide by the sum of resistors in this series circuit, and you multiply all of it by, the voltage source, R equivalent. This is going to give you 3 ohms, right, over 3 ohms plus 1.05 ohms, right, times 2.11 volts, and this should give you 1.56 volts. Or we can simply use Ohm's law, where we know VL is simply going to be the product of the current times the resistance, which is simply going to be IL, which is 0.52 amps times 3 ohms, and this gives you 1.56 volts. So guys, this is Millman's theorem applied to this circuit. I hope I helped clear any doubts about this theorem. Thank you.